Hello. Today I'm going to be talking to you about exciting changes in our understanding of a planetary satellite called Titan. Within the Milky Way galaxy is our little solar system, consisting of our star, the Sun, and many other things bound to the Sun by gravity. These include the 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, each of their respective moons, dwarf planets such as Pluto, and millions of smaller bodies such as asteroids, comets, and meteorites. Our solar system is host to a huge number of exciting conditions that are of interest to physicists back on Earth. An atmosphere that is of particular interest is surrounding a moon called Titan, the largest of Saturn's 82 moons. It is the second largest natural satellite in the solar system, after Jupiter's moon Ganymede, and is 80% more massive than our own moon. It is actually larger in size than the planet Mercury. It is the only known moon to have a dense atmosphere and is commonly described to be planet-like. It's thought that Titan's life began as a mixture of methane, water, and ammonia, along with an unidentified rocky core and an ammonia-water ocean. As the satellite developed and stabilized, the core warmed up and expanded, resulting in an increase of pressure. Titan's core is believed to have a pressure of between 2 and 6 gigapascals. 2 gigapascals is equivalent to the pressure you would experience 200,000 metres under the sea, or to the weight of 32,371 large African elephants sat on 1 square metre of land. The particular mixture within Titan's atmosphere that physicists are interested in is called methane hydrate, where hydrate simply means that the mixture contains water. Scientists previously thought that methane hydrate was not stable at high pressures, and when exposed to these would separate into ice and gas, meaning that upon the core's pressure increase, methane gas would be released into the atmosphere, and solar radiation from the sun would have removed all its remaining traces. The problem with this theory is that the current atmosphere around Titan has an abundance of methane gas. The previous explanation for this was that there must be some source of methane on the moon's surface, such as a lake. Now, however, we know that methane hydrate can exist at these pressures, and scientists believe that various stable forms of methane hydrate have slowly risen through Titan's core over its lifetime to produce a subsurface layer of methane hydrate. Just like water has a phase transition and turns into ice at low temperatures, similar things can happen at high pressures. Methane hydrate has 2 phase transitions to different types of solids at pressures of 0.9 and 1.8 gigapascals. Now we understand exactly what happens to pure methane hydrate within environments similar to those on Titan. The next step to understanding its full atmosphere is to add another molecule commonly found there into the mix. The question posed by physicists was this: does ammonia make any difference to how methane hydrate behaves at high pressures? We can find the answer to this question by recreating the extreme conditions found within Titan in a laboratory slightly closer to home. We do this by squeezing a sample of the mixture we want to test in between 2 diamonds. This is a useful technique for several reasons. Firstly, diamonds are among the hardest naturally occurring materials on Earth. This is useful as it allows us to reach very high pressures without worrying whether the diamonds are going to break. They are also transparent, which means that we can see what might be going on in between them using a microscope. This technique relies on the simple equation: pressure equals force over area. If we squeeze a very small sample, we don't have to exert a large force upon it to achieve a large pressure. The sample can be monitored with scattered laser light, which can provide physicists with information about the bonds holding the molecules together. By using these techniques, we now know that ammonia seriously impacts methane hydrate's ability to change phase. When ammonia is present within the methane and water mixture, instead of changing phase at 0.9 and 1.8 gigapascals, methane hydrate transitions instead at 2.4 and 4.0 gigapascals. This is more than double the pressures that we were expecting. This is an extremely exciting result, as it means that we are one step closer to truly understanding planetary life. Thanks for listening. Who knew life on Titan could be so exciting?